You ever have to make a huge decision when you don't have all the facts? Of course you have, right? We do it constantly. But when the stakes are high, in science, in medicine, we can't just wing it. We need a solid way to let the data guide us. So let's dive into the story of one of the most powerful and, most controversial numbers in all of statistics.
And that's really the core question, isn't it? We've only got a sample, just a little peek at the truth, never the whole picture. So how do we use that little peek to make a big call? To launch the product, to approve the new medicine? Well, it all starts with a framework that feels a whole lot like a courtroom trial.
You see, in any statistical test, we start with a default position, the status quo. We call it the null hypothesis. And it works just like in a court of law, where someone is innocent until proven guilty. That's our null. The alternative hypothesis, well, that's the challenge. It's the prosecution's claim that, no, something else is going on. The accused is actually guilty.
Now, this is a super important point. We're never trying to prove that the null hypothesis is true. You can't really prove innocence, right? The burden of proof is on the challenger. Our job is to see if the data we've collected is strong enough evidence to reject that status quo, to overturn that presumption of innocence. But just like in a real trial, any decision we make could be wrong.
This little grid lays out all four possibilities perfectly. Look, if the person is innocent and we let them go, perfect. If they're guilty and we convict them, great. Those are the right calls. The trouble is in the other two boxes. We could convict an innocent person, that's a type I error. Or we could let a guilty person walk free, a type 2 error.
And you've got to understand, the type 1 error is usually seen as the worst mistake you can make. It's a false alarm. It's sending an innocent person to jail. It's announcing a scientific breakthrough that turns out to be nothing. Because it's so serious, we have to decide before we even look at a single piece of evidence how much risk of this we're willing to take.
And that's where alpha comes in. Alpha is our significance level. It is our line in the sand. It's our standard for reasonable doubt. We say right up front, okay, I'm willing to accept a 5% chance of making a type 1 error, and no more. It's a promise we make to ourselves. But making that promise has a direct consequence.
Yeah, this is the classic, unavoidable trade-off. It's kind of like a waterbed. If you push down on one side, let's say you get really strict to lower your risk of a type 1 error, the other side just pops right up. Your risk of a type 2 error, of missing a real effect, goes up. There is just no free lunch in hypothesis testing.
Okay, so this theory is all well and good, but how does this actually play out in the real world? How do we measure the evidence from our data? Let's walk through a classic engineering problem and see it in action.
So, picture this. We're testing rocket propellant. The spec sheet, our null hypothesis, says it should burn at an average rate of 50 centimeters per second. We grab a sample of 25 batches and find the average is actually 51.3. Is that difference just a random fluke, or is it a real sign that something's wrong with our process? Well, we run the numbers, and we boil all that data down to one single number, a test statistic. It's basically a score for our evidence. In this case, our score is 3.25.
So we've got this number, 3.25. Now, based on our 5% alpha level, we already figured out that any score more extreme than 1.96 would be enough to reject the null. And our number, 3.25? It's way, way out there. It's deep in what we call the rejection region. We've got enough evidence to convict. But this makes you wonder, doesn't it?
I mean, we know our result was unlikely enough to cross our line in the sand. But can we be more precise? Can we put an exact number on just how surprising this evidence is? Instead of just a simple yes or no, what if we could actually measure the strength of the evidence itself? And this very question is what leads us to the p-value.
And here it is, the p-value. At its heart is a measure of surprise. It asks a simple question. If the null hypothesis were totally true, if the real average burn rate was 50, what are the odds that we'd get a result as wild as the one we just saw just by pure random chance? So a tiny p-value means our result was super surprising, which makes us really start to doubt that null hypothesis.
And for our propellant data, the p-value is 0.0012. I mean, that is tiny. That means there's only a 0.12% chance of seeing a sample average this far off the mark if the true average really was 50. The data isn't just talking, it's screaming that something is going on. And this leads us to a really simple, elegant rule for making our decision.
And here's what makes the p-value so incredibly useful. We just compare it to our alpha, our line in the sand. Our p-value is 0.0012. Our alpha was 0.05. Since the p-value is way smaller, the evidence we found is much more surprising than our threshold for reasonable doubt, so we reject the null hypothesis. The propellant is definitely not burning right. That's it. It's that simple.
Okay, so we've got this amazing tool and a clear rule for using it. And honestly, for a lot of day-to-day work, that's all you really need. But if you want to go deeper, if you want to get to that PhD-level understanding, you have to ask a tougher question. Where did that test, the one that gave us the p-value, even come from? What makes one statistical test better than another? Now we're going into the deep theory that holds all of this up. So, deep down at the very core of all this theory is something called the Neyman-Pearson lemma. The best way to think about it is like a recipe book. It gives you the mathematical instructions for building the absolute best, the most powerful test you can for a given situation. For the alpha you chose, this lemma shows you exactly how to build a test that gives you the best possible chance of finding a real effect. And this isn't just some clever rule of thumb. This is the bedrock of the entire field. This is the deep, rigorous math that's studied and proven in top research universities. It's what gives us the confidence that the tests we're using aren't just pulled out of thin air. They are mathematically optimized to be the best possible tools for the job. Now, the absolute dream is to find what's called a uniformly most powerful test, or UMP test. This is the statistical holy grail. It's a single test that's the best, not just against one specific alternative, but against every single possible alternative. It's the one test to rule them all. But as you might guess, they are incredibly rare. For most complex, real-world problems, a single UMP test just doesn't exist. So what do you do then? Well, this is where statisticians get really creative. There's a whole field of research dedicated to finding the next best thing. You know, if we can't be the most powerful against everything, maybe we can find a test that's the most powerful on average, or one that's really, really good at detecting small changes. It's a fascinating puzzle. And this really brings it all together. Think of the p-value you get as a messenger. It's delivering you a result, but how much you trust that message depends entirely on the source. The power of the test that generated that p-value, well, that's the strength of the whole army that the messenger represents. A tiny p-value from a powerful test, now that's a message you can take to the bank. So, there you have it. We've gone from a courtroom to a rocket factory all the way to the deep theoretical heart of statistics. We've seen that the p-value is this incredibly elegant, powerful tool for weighing evidence. But we've also seen that it's just one piece of a much bigger story, a story about risk, power, and our constant search for truth in a world that's filled with uncertainty. So, is a single number ever really the whole story? Now that's a question worth thinking about.